going into the contact, and this is what we'll spend most of our time in this class, is talking about contact forces, because really the gravitation, law of gravity and non-contact is a constant. So it's negative 9.81 interacting, and you'll see that from the body weight. So the first one of our contact forces is reaction force, and that is basically the interaction in equal and opposite that we talk about, of how I'm interacting with the surface I'm moving on. Whether it's the asphalt, whether it's the grass, whether it's a pool, whatever it is, there's a reaction force of me interacting with it. The most common we talk about in our world is ground reaction force. And what I would refer the ground reaction force to is F subscript GRF for ground reaction force. And then because there's three directions, you have a Z, an X, or a Y. So I would actually subscript that X and Y. Some people would simply do FZ, some people do FX, some people do FY, but I always do GRF so I know which one I'm talking about. Okay, but this is an example of a ground reaction force. Here you have underneath this person, you have a force plate. This person has a center of mass coming down, right? So this is the force due to gravity. It's a negative force. And then there's going to be equal force coming this way, which is the force of GRF in the Z component. Now, what this looks like is if I did so this would be a vertical equation. There's vertical components of this coming up and down. And so if I did the sum of forces equals MA in the vertical, sum of forces in the vertical, then it would be this. Force body weight is a negative force plus the force GRF Z equals, if this person was standing, it'd be 0. Why would it be 0? Well, MA on the left-hand side, if they're standing there and not moving in the vertical direction, then A equals 0. Therefore, this equation equals 0. Okay? Now, if there's movement happening, and I had F body weight negative plus F GRF Z equals MA, I would know what the A is from my equations. I would know what body weight is, and I can calculate what the ground reaction force should be in order to cause that motion. This is how we take that F sum of F equals MA. But just notice that ground reaction force is going to be the interaction, the vertical component, or anterior, posterior, medial, lateral. So there's three here. Okay, so this blue one is the vertical component during walking. Black one is anterior, posterior, so braking into propulsion. And then the medial lateral is the horizontal sway. Okay, so this is how it breaks up into the Fx, Fy, and Fz components. So as we watched in that video, the runner ran in this direction. So they moved from left to right. And you found as they hit the force plate that there was a ground reaction force pattern or an arrow that followed their motion throughout the process. Now, this arrow would decrease and decrease, increase and decrease in magnitude and direction throughout the process. So if we broke it up into the components, and again, these components are F, GRF, Z, and you can see here it was just the FZ. Here's the Fy, and here is the Fx, because that's the only force they're talking about is the ground reaction force in this image. When you look at it here, it has vertical, anterior, posterior. But so when we do this angle of this person running this way, and we follow that pattern, we break up that arrow, we decompose it into three directions. Vertical, anterior, posterior, medial, lateral, and that gives us these three components here. So when we talk about this and we talk about creating the equations as we get to the free body diagram, you will break them up into the sum of the forces in each one of these directions, X, Y, and Z. A lot of times we're only going to have you do X and or Z and Y or Z and X, the vertical and the horizontal component. I won't have you do medial lateral because those are a lot more difficult to play around with. But keep this concept in mind when we get to the ground reaction forces coming up. But you'll have, as the person was running this way, you see them create the ground reaction profile. This profile is deconstructed into this here, which is the three components of the ground reaction force. So now if you look at what we're going to do along this process is you'll see the non-contact up here doesn't change the law of gravitation. And then you're going to see the contact forces up here. As far as the reaction forces, I put ground reaction because with me, that's mostly what we're going to deal with. But there's also the reaction if you push on a wall. If you're holding a bat, there's a reaction force between the bat and the hand. But for most right now, if I'm sitting on a bike, there's a reaction force between the seat and the person. But ground reaction force is what we're going to use for mostly going forward. But one of the next ones that we have is a joint reaction force. And the joint reaction force is describing what's happening with inside of the joint. And that is composed of a compressive force and typically a shear force. So on the surface of the joint, you have this compressive force between bone and bone. So the femur, and in this case the tibia, are pushing against each other in a particular, creating that compressive force. But there's also a need for this fibia to go this way in the shear force, and it's creating what we call a joint reaction force, which is a force that's being created inside of the joint segment from the bone-on-bone reaction. And this is very important as you go forward and you're doing inverse dynamics, and you look at, if you look at PFP, if you look at iliotibial stress syndrome and some of the knee injury components, this is where that impact force creates this joint reaction force depending on the kinematic positioning of the leg. So a more flexed leg has a different joint reaction force of a leg that's more stiff. And the true component is whether it becomes more in the compressive or more in the shear dynamic of it, what's happening with the joint reaction force. Taking it a step further, we're going to talk about another contact force, and that's the force of friction. So if I take you back to thinking about the previous slide where we talked about, or 2 slides ago where we talked about ground reaction force, and remember that there was that horizontal component that was the anterior posterior ground reaction force, which is the foot interacting with the ground in that horizontal direction. So you have a braking and then a propulsive force is typically what we call that in the AP direction. But in order for this to be represented by the ground reaction force, right? Remember, it's an equal and opposite force of the way that we're behaving on the ground. Then there has to be some ability for the ground to push back against me. And this is where the frictional force that we're going to talk about here comes into play. Because without friction, these two, the foot and the ground, wouldn't be able to interact in the horizontal component. And that's because the frictional force is a force that runs parallel to the 2 interacting surfaces that opposes the direction of impending motion. Now, this concept of impending motion is extremely important, this right here. And really, it refers to what is the impending motion. In the AP direction in the foot and the ground, it's actually the motion of the foot, not necessarily the motion of the center of mass. Which is creating that interaction with the ground. Now, the magnitude has a lot to do with the magnitude and position of the center mass of the system, but at that location, it has a lot to do with the impending motion of the foot going over the ground or the surface of which you're running on. So I think it would be impossible to generate that horizontal propulsive force or braking force when you're walking if the ground and the interaction between the 2 surfaces was frictionless. And that's very, very important, right? So frictional force, if we look at this equation, is going to be proportional to the normal force. And that's what, in this equation, the N is. N is normal force. And what normal force is that is the force that is perpendicular to the 2 interacting surfaces. And these force actually keeps the 2 surfaces together. So in the instance that we're talking about, the person interacting with the ground of the foot, you have the forces that are acting are, again, body weight and the vertical ground reaction force. So the vertical ground reaction force is the actual normal part, and that's perpendicular to this frictional force in the motion aspect of it. Okay. Now the other component here is this mu. And that's what it's called mu. And that's the coefficient of friction. Now this is a dimensionless number that is descriptive of how the molecules of each of these 2 interacting surfaces interact or behave with each other. And the greater this magnitude, so if the mu has a higher number, then that means that the 2 surfaces have a great interaction. If it's lower, that means there's less interaction. So the frictional force decreases or reduces. Think about ice versus walking down the road without the ice surface. The ice or the frozen water it reduces that interaction or that coefficient of friction. We'll talk more about coefficient of friction in a second, but this is what I want you to focus on here. So friction, parallel to the interacting of the two surfaces, and it opposes the impending motion of the interaction. And the normal force is perpendicular to the frictional force. And the normal force keeps the two interacting surfaces together, keeps them interacting. Without the normal force, they would not be interacting together. And the coefficient of friction is dimensionless, and the higher number, the greater interaction between the two surfaces. So now I'm going to use this block example. It's a very traditional physics example, and I don't like to do it, but I'm going to, right? So if we have the block, the impending motion is this way, from left to right on your screen. So this is the force due to gravity or the force of body weight, right? And then you also have a force coming up, which is the vertical GRF, and that's that force. Now, this is also going to be called, in this instance, force of normal, okay? So the person is pulling, it's a tensile force this way. So remember, the impending motion is here. Therefore, your frictional force is going this way. Okay? So this is a diagram of what's happening. So if you put the normal force and the frictional force, there's that 90-degree angle. And without that normal force of body weight, force due to gravity, you would not have these two interacting together. Now let's look at it, how it relates to human motion. And I'm going to start by looking at the orange person running. And so remember that we have the ground reaction force, or the force due to ground reaction, and there's an X, a Y, and a Z component. The Z is the vertical, and in our case, let's have the Y be anterior, posterior. And so we'll have the X medial lateral, but we're not going to talk about that. So in this free body diagram, you have, it's interesting because the grays are supposed to be some of the external forces. The oranges, I anticipate, this isn't my diagram, so this is me interpreting it. The oranges are supposed to be the forces that the body is exerting on the ground. So for me, the normal force here and the propulsive force should be opposite, where the person is pushing down, and that should be the propulsive force this way. And then the reaction force, or the normal force coming up, is the gray one. So what we're measuring with the ground reaction force or the force are the two gray ones, in my opinion, which is this propulsive force, or the force of friction, and then upward, which is the vertical ground reaction force. Okay, so the idea is the person is pushing backwards, so the impending motion of the foot across the surface of the ground is back. If there was no friction, the foot would just slide out from underneath the person. Let me show that. Let me see if I can clear this up and show you that. So remember, this person is pushing on the ground this way. So if there was no friction, and the friction is going this way in this case, which is correct, and it's actually very similar to the ground reaction force, the AP, but if there was no frictional force, the foot would slip and there would be no ability for this person to generate the horizontal motion that they need to do. Okay, so that is where this frictional force comes into this component. And the normal force for me would be the vertical ground reaction force coming up, which I would have to switch, but don't worry about it. Here's another schematic for it on figure 2, where we talk about it from an individual leg perspective and take everything else out. So the R and the R are the resultant vectors for the ground reaction force, including the vertical and the AP. The vertical is the G, and F is the frictional force. Okay, so if the person's center of mass is straight up and they're standing there during mid stance, then typically you have this completely vertical component, and you don't see any frictional force going, because at this point is where, if I had the graph, the AP would be crossing the line at 0. So there'd be 0 anterior posterior ground reaction force, because at this point there's no need for a resistance, because you're not pushing forward or backward. In the other instances, in C, which is this one here, the ground reaction force is becoming a propulsive ground reaction force. The foot is looking to push this way, but we're modeling the frictional force as the AP ground reaction force. So force of friction equals the force of the AP ground reaction force. Okay, and so that's where it's represented. So when we do a measurement with the ground reaction force, the pushback of the AP direction of the force plate generally, if we're on level surface, represents how much of the frictional component. And what happens is a lot of times we'll do friction as the ratio between the AP and the vertical. And how does that, or sorry, the mu, the coefficient of friction. And how does that work? Well, if the frictional force equals mu times the normal, sorry, that's times, then if I take the frictional force over here and I use this as the AP, I'm going to write that better for you because that's confusing. So if I take the original equation, the force of friction equals mu times the normal force, okay? And I want to isolate the coefficient of friction, I can say the force of friction over the force of the normal. And in our world, this is AP GRF over vertical GRF, ground reaction force. So if I'm measuring on a force plate their response to an activity, I can calculate what's happening in the coefficient of friction between my foot or the shoe and the ground and the force plate by identifying the ratio of the anterior posterior ground reaction force and the vertical ground reaction force. That's why I'm saying the normal force should be the one coming up, because that's what we're measuring. At this point, we're ready to take friction, the frictional force, or the force due to friction, and divide it into the two components. And there's two components that relate to whether the object is in motion or whether the object is stationary. The first one will be static friction. And what this is you'll see on the first part of this graph here, you have a static component here and you have a dynamic here. Dynamic means in motion, static means not moving. You'll see this linear trend that travels upwards here of the static friction, and then you see it drop at the instant of motion into a constant dynamic friction or kinetic friction at that point. And so static friction is essentially the frictional force that occurs during stationary movement. And this means that the applied forces are not great enough to withstand or overcome the force due to the friction, whereas the coefficient of friction or static friction as well as the normal forces. At some point in this motion or in this event of the application of force, you reach this moment of instant of motion, and that maximum static frictional force is referred to as the limiting static frictional force. So there's a value there, and at the moment that you are trying to apply force to something in the parallels of two surfaces or even vertical, but you're reaching that horizontal component of it, then you're going to achieve a moment where it begins to move, and that is you found its limiting static frictional force. Okay, then you see a drop, and through some numerous studies and numerous applications, we found that the coefficient of kinetic friction is less than the coefficient of friction of static friction. So if I did this, mu k is less than mu s. So just know that your coefficient of friction and kinetic friction is less than your coefficient of static friction. And that is, so as we're moving, the frictional force is still opposing the motion or in contending motion, but it is less than the static friction. Now, the kinetic friction is also referred to as your rolling friction as well as your sliding friction. So these are each examples of what a kinetic friction are. So this rotational friction is what we just talked about as a kinetic friction, and it's resistance to rotational or twisting movements. These are like the wheel or anything that is rolling on top of bearings, things like that. And again, this is less than your static friction because it's actually in motion, and that is an important aspect of it. One of the next components we're going to talk about are the fluid resistance aspects of motion. Most of human motion takes place in two environments, air and water, or gas and liquid. And so these are components of human motion that are involved in resistance or affecting how we move through our environment. And so as we look forward to this, the couple properties that affect how we interact with our environment are the density of that environment, or the mass per unit volume, and the viscosity of the fluids around us. So how dense the air is, or how dense or viscous the fluid is, right? So viscous fluids, there's a difference in viscosity from the salt water in the ocean to swimming in a lake. Okay, there's a difference in density of the air at sea level than there is up in Mount St. Helen or the Matterhorn or any of those high altitude places. And so the biggest, or one of the very first that we're going to talk about, we're only really going to talk about two, and we're only going to touch the surface of them, is this component of drag. And drag is the fluid resistance that always acts to oppose motion. So it's very similar to our components of friction, although there are many components here that take place. So if we look at this, you'll see many different variables on the right-hand side that have an effect. And in the CD is the coefficient. So this first part of the equation right there is the coefficient of drag. So that is given through just whatever material we're moving through. And then you have this A. The A is going to be the surface area. So how the object is approaching or traveling through. And this, an easy one to think about this is, think about cycling. And think about triathlons versus a road bike, or if you look at the elites and you really look at how they cycle, they're always crouched down. They get the elbows in, they get really low, and this is because they're trying to decrease that surface area, which also decreases the air resistance in the form of drag. Okay, and the rho, or that P, is the fluid viscosity. So the next one in this line here is rho, and that's fluid viscosity. And then we have V squared, which is the relative velocity of the object. Okay, so this is that idea of how fast I'm moving through it. This comes into play, I think, taking the cycling concept again, as you're trying to thinking about what helmet to buy. If you want to get one of those real fancy aerodynamic helmets, well, it really depends on how fast you're going. So if you look at the research oriented behind it, what they say is unless you are traveling a certain velocity, you're not getting the effect or the maximum effect of this point. So that is what we just talked about, the drag component. And that is what is going to resist motion, or tend to resist your motion in which you're going. So we look at this swimmer here on the right-hand side. You'll see a couple different forces, right? So you have the force of body weight, so it's at the center of mass down. The drag is going the opposite way of which the thrust is going. So this hand comes back to the water, and it's producing a forward motion this way. And then there's that force of drag that is going the opposite direction. Okay. Now the other one we have, if you look back over here in the graph, is this lift component. What the lift component is it's perpendicular. So it's kind of like, think about your normal force, but it's a lift component that brings you up. Okay. And that is going to be what we refer to oftentimes as, in swimming, as buoyancy. So how buoyant you are. And then, so what you'll have is you'll have this fluid resistance vector that is comprised of the two components at a right angle. Now, it's important to note that the buoyancy, or the lift component, only occurs under certain circumstances. And that's typically when an object is spinning. So give a golf ball or a baseball, or the way you kick a soccer ball. So as those balls are spinning in the air, And that, think about a curveball versus a knuckleball, if you know baseball pitching, and how they float and flutter through the air versus how they have a Jurassic movement pattern through the air. And then as well as if they're not perfectly symmetrical. So think about the wings on an airplane, or different components of a bike, now how we're trying to make bikes. But these are all aspects of buoyancy that need to be there in order for it to occur. Now, at this point, you have learned about a few forces. Now, I only touched the surface and categories of forces. So now we have to start thinking about what actually the forces are and how they are interacting with the body. So we have these things called free body diagrams. Now, this is going to be a method for you to illustrate and identify different forces acting in the body so you can create the equations of motion. Now, the equations of motion are simply going to be the sum of the force in whatever direction, x, y, or z, equals the mass times the acceleration in that same exact direction. So we look at all the forces that act in a direction, and we can talk about how those cause the movement in that direction. And how this is represented is it's a stick figure. So you just write a simple stick figure. This is not an artistic class or a process. So you do your stick figure, and then you identify the vectors representation. And in the key component, I have it highlighted, I have it underlined, capitalized, is external forces. So you're not going to put muscle forces. You're not going to put the joint reactive forces. So these are all things you're not going to put on there. You're only putting external forces. Force due to gravity, normal force, a ground reaction force, force of one object on the other. And that's acting on a system. It is important to understand, just like your reference systems, that you define what your system is. When I ask you these questions, you need to make sure that you define what, or you understand what your system is. Whether it's the bike and the person is one system, or the bike and the person are two separate systems. That becomes a very important detail, and then we'll talk about that a little bit as well coming up. But let's take this for example. Here I have a runner. If I asked you during this point, and let's say it's foot contact, so that left foot, or the right foot, sorry, the lead foot, this one here is just in contact with the ground. I'm going to ask you to give me a free body diagram of that. So I want you to go ahead and think about that for a second. Okay, that's it. And now let's do it. So I have 4 forces acting on this person. And what I've done is I've put the forces where they are on the person. Now, it's important to note that if we did a ground reaction force, the ground reaction force would be like this. It would go back towards the system. But in this process, what you have to do is decompose that. So here's the vertical component, and here is the AP component, right? So these two vectors, vector 1 and vector 2, are a decomposition of that ground reaction force vector. So if you give me an angular vector like this, then it's going to be wrong because you need to be able to break it up in the x, y, and z components, okay? So this is what it would do. I would want you to label what each one of these are. So I have F air, which means there's air resistance, because look at, if we look at this, the motion is going that way. And typically, I'll give you a motion vector saying this is the impending or anticipating motion. The force of body weight is acting at the center of mass. The ground reaction force in the Z is at the point of contact. Same with ground reaction force in the Y. Now, this is the interesting part is, for me, for years, I've done also a force of friction, but we can talk about that in class on where I have stopped doing that and why I've stopped doing that. Now let's think about what I talked about just a second ago with understanding what the system can be defined by using the bike and the rider as one system. So in this situation, I want to know this situation. Bike and the rider are one system. That means they're combined as a unit with their interaction with the ground. What does this look like and how would this differ? And during this process, I want you to start thinking about how would this differ if I said I want to know the interaction between the bike and the rider. Okay, but in this point, I want the bike and the rider as one system, and I want to know their interaction with the ground. So here we have the force due to the weight, and I called the body weight here, but I'd say it's system weight. Here we have both forces of the ground reaction force in the vertical direction. And what we do know is that these two forces should be equal and opposite the one coming down because the person is able to ride and stay up. Here we have the rolling frictional force. And the interesting part is this, and this is what I want you guys to make sure you understand. The person is going this way, but I've told you that frictional force is opposite the direction of where the person is going. So why are these two frictional force vectors going in the direction of motion of the system? Well, that's because the rolling friction opposes the motion of the bike tires, right? So these frictional forces go opposing the direction of these tires, and so it's going to the right. And then the final one is going to be depending on force of resistance or drag. And so remember, these are components of the coefficient of friction, the surface area given why this person is crouched, elbows are in, trying to create more of a ball where the air would just row around him, the velocity squared, and the rho, or the density of the air around him. Now, I would like you to think about why or what would differ with the interactions here if I was talking about the cyclist versus the bike as a unit.